Hey Finxters, and welcome to this tutorial where I will guide you through the tutorial with the topic what is an array in computer science. So this is more a conceptual topic, but it's very, very important, very critical to understand for every coder, for every upcoming computer scientist. So I thought it would be valuable to create this tutorial where I will show you like everything you need to know to get started, to get a conceptual understanding of an array in computer science. So let's go to the drawing board and start conceptualizing. Okay, what is an array in computer science? An array is a data structure. So data structure means it holds some data and it has some advantages and it has some disadvantages. And the data structure is organized as follows. So you have a bunch of cells, you can call them cells, that are ordered in a subsequent way. So it's a bunch of ordered cells, and each cell has an index that you can access. Okay, so for example, this cell has index 0, this cell has index 1, this cell has index 2, 3, and so on, yeah, until we reach the maximum index of the array. Okay, so this whole thing would be the data structure. The data structure means just as the name suggests, that it structures some data. Okay, so and what kind of data does it structure? You can put anything into an array. Okay, so usually in the operating system, so this is your random access memory. So this is your memory on your computer, and somewhere on this memory resides this array data structure. And usually arrays are very efficient because these cells, they reside close to each other in your RAM. Okay, so they are close to each other, so the access is very fast actually, yeah, because usually, so if you access some chunks from memory, you usually access big parts of the memory at once. Okay, so I mean, this is not so critical for random access memory, it's more critical for disk memory, but still, if you have data that is close to each other, the access speed improves. Okay, so an array resides as a data structure residing in your operating system. Let's remove this thing because I need some space. Okay, so and actually how it consists is each cell in this array is a pointer to an object. So therefore you can have any object in your memory. Okay, so this is how an array is structured. Okay, so each cell is a pointer to an object, and the pointer actually, so what is a pointer? A pointer is just a memory address. So say it's like a hash value of, I don't know, 12f or something like this. Yeah, so it really doesn't make a lot of sense, but think of it this way. So it's a hash value, or it's a binary number in the end. So it's a bunch of ones and zeros that just encode the memory address of the object's location. And now the object can be arbitrarily large, yeah, because this array just stores, so the information stored here is just a bunch of like a fixed number of ones and zeros, and something like this, yeah. So we have some ones, some zeros stored in this array data structure. So an array cell always has the same size, which is just the size, the number of bits you need to encode this pointer. But then you have, you can point to an arbitrary object basically, yeah. So and this can be any box. It could be even another array. So you can have an array of arrays or so. Okay. So this one could be just an integer, say number 3, or it can be an array, or it can be anything really. Okay. So and so for example this one. So this is like the miniature. A miniature array with some pointer by itself. Okay, so it can be really meta, where an array cell consists of points to another array object that has some pointer to other objects. So you can also have an array of an array of an array of an array of an array and so on. Okay, so you can have arbitrary complicated data structures here, but usually the restriction is that an array has homogeneous cells, or cells of homogeneous data type. This means that all the cells have the same data types usually. So of course this is not required. It's not a strict conceptual requirement. So there can be different programming languages that handle it differently. But so for example in Python you can have arrays are usually represented by lists. So this is just called a list, but a list is the underlying data structure for a list is an array in Python. So so you can have a list of lists or you can have a list of integers, or you can have a list of some mixed data type, a list of integers, floats, and so on. Okay, so you can have, for example, here you can have an integer, you can have another array or list type. Here you can have a float, for example, 3.14 number of pi. Then you can have a string in this cell. Okay, so this one could be the string hi, for example, yeah, and so on. So you can have pointers to all kinds of objects. So this is what an array is really. Okay, so it's just a data structure in your memory. And so here I have visualized this again, and you have some cells, you have some elements. So everything within the cell, the objects within the cells are called elements, and the cells themselves, they are called array cells, and you can access individual cells with these indices. Okay, so what does it mean you can access it? So let's have an example in your code. So say we have an array called friends. And we have like Alice, Bob, and Carl, and maybe another one, say Anne. So we have 4 people in our array, friends, and now we can print friends 0. So this would be the first element. The result here would be Alice. Yeah. Then we can have print friends 1, and here the result will be Bob. Then we can have print friends 2, and the result would be the third element, which is Carl. And then we can have friends, just going over this slowly so that you really understand indexing, like this. Okay, so we have, this is called zero-based indexing. Why? Because the first element is 0. Okay, so all indexing is based on the first element 0. I mean, this is arbitrary. The first element could also have, theoretically could have the index 10, for example, yeah? And then you would just count starting with 10. But it's particularly in programming languages, you like in 99.999% of the time you start counting with 0. So the first element doesn't have index 1, it has index 0. Okay, so if you want to access the first element, you need to pass index 0 into the array. Okay, and again, this is a Python list that I have created here, but list, the underlying, so the implementation of a list is, so Python is implemented with C Python, for example. My Python implementation is based on C Python, so C, the programming language C, and C++ implements the programming language Python, and so the implementation of the list data structure makes use of arrays. So the underlying implementation of Python lists uses arrays. So therefore, you cannot differentiate really. I mean, you need to understand the concept of arrays before you can really understand the concept of Python lists, for example. Good, so let's go back to the article. So we have, what is the definition? The formal definition is an array is an ordered collection of elements indexed by contiguous integers. Okay, so it's ordered, the elements have an order and the order is fixed. Yeah, so it's not like a set, for example. A Python set is a collection of unordered elements. They can have any elements. So for example, if you throw in 3 values into a set and you print the set, the order may be completely different. So the set doesn't guarantee a fixed ordering, but an array is ordered. Okay, so here you have this ordered number of elements. This order will always remain. It will never change, and it will be predictable. And yeah, it's ordered. Then we have elements. So an array consists of elements, and in the vast majority of cases, the elements are of the same type. But for example, there are also major programming languages like in Python, where that allows for this dynamic and heterogeneous typing of lists. So a cell can have one type at like so for example here we can have, let's go back to the example here. If we run this example, we get the following output, yeah, Alice, Bob, Carl, and Anne. So now if you again print friends 2, we get Carl. So this is now of type string. So the cell has type string, but now we can also set the second cell, the third cell with index 2 to say an integer. Yeah, set it to 42. And now if we print friends, you see the third element with index 2 is now of type integer. So previously it had type string, but now it has type integer. So the type has changed. So therefore it doesn't require that the type is static and they will never change. In Java, this is the case, but in Python, this is not the case. Okay, and this is not a requirement of the definition of arrays. Array just must be ordered. It must contain elements, and it must have contiguous indices. Okay, and what does this mean? This means that the index starts with 0, and then you have like all integers from 0 to the length of the array. Let's call it n minus 1. Why minus 1? Because we start counting with 0. Okay, so if you have n elements in the array, we would start, if you would start counting with 1, then we would have 1, 2, 3, 4, 5 until we reach n. Then we have n elements, but we start counting with 0, so we need to shift all of them. Okay, so we start with 0 and we end with n minus 1 included. Okay, so the last n minus 1. So if you have n elements in the list, the last index will be n minus 1, and the first one will be 0. And we have all those indices. So all numbers are assigned to one element. Okay, so this index is assigned to this element or this cell. This index is assigned to this cell, and so on. So, and this is like an assignment. Each integer value, that's why it's called contiguous. Each integer value is assigned to one cell, exactly one cell, and there's no hole or something. Yeah, so we don't have a situation where, say, an index, a number x. So we have here we have number x minus 1. Here we have number x plus 1. And say x minus 1 points to one cell and x plus 1 points to the next cell, but x doesn't point to any cell. So we don't have this situation. This can happen in a hash map or so, or in a dictionary you can have something like this, but for arrays you don't have a situation like this. So we have contiguous indices. Okay, so you may ask, what are some applications of arrays? And there are too many to name, actually, yeah, because arrays are at the core of actually more of all algorithms. So I challenge you, give me any algorithm that doesn't rely on arrays in one way or the other. It's really hard to even come up with one. So arrays, for example, implement mathematical vectors. They implement multidimensional matrices. They implement other data structures, even like lists. You have seen in Python lists rely on C++ arrays in their implementation. Many sets are based on arrays, hash tables, stacks, and many more. And so, for example, if you use any of those data structures, you implicitly use arrays. So you need to understand arrays to really dive deep into the data structures. Arrays are also used in representing graphs. So in graphs you have adjacency lists and matrices that represent graph data structures, okay? And all the application of graphs. So what is a graph? So maybe have a very quick excursion to graphs. So graph is something like this. So you have some vertices and they point to each other. For example, this is a vertex, this is Alice, this is Bob, this is Anne, this is Liz, and this is Carl. Now say Alice in Facebook, Alice has a friendship relation to Carl, and Carl has a friendship relation to Liz. Liz maybe is friend with Anne and Bob, and Alice, and Alice is also friend with Bob. Okay, something like this. So this kind of networking structure, this is called a graph, and graphs, there are many ways of representing graphs in computer science, but one way is via an adjacency matrix. So what is an adjacency matrix then? It is based on an array. So say we have 5 vertices in the graph, then we have each vertex has an integer associated to it from 0 to 4. So we have 5 vertices. First vertex, say Alice, this one is Alice, has index 0, and say this is Liz, Liz has index 4. Now we have a matrix. Okay, something like this. So we have this matrix, and now cell ij, so say this cell 2, 3, this one is 1 if there is a relationship from vertex 2 to vertex 3. And so there's always a relationship from vertex I to vertex I, because I mean the vertex knows itself. There's an edge, there's so one relationship here. There's always a relationship from a vertex to itself, say. Okay, so this would mean that on the diagonal, so these values would always be 1. But then you can also have zeros. For example, if there's no edge from Alice to Liz. Yeah, so let's check the graph again. There's no relationship from Alice to Liz, and therefore the edge, so the adjacency matrix would contain the value 0 here. Okay, so the adjacency matrix has a bunch of zeros and ones, and they, like this representation, this, if you have this matrix, this is basically can be represented by a graph or the other way around. So you can represent the graph and adjacency matrix. They are actually identical in terms of the information they provide. So you can transform one in the other and back, and you don't lose any information. So this one is the same as this one here. It's the same data, but it's just a different representation of the data. It's one way of representing a graph in your computer. And of course, on which data structure does this rely? On an array. Okay, and now you may ask, okay, what is the application? What are some application of arrays? You can ask, what are some application of graphs? And if you check out this, I mean, there are so many applications of graphs. I've even written a whole article about this. Let's open the article. So there are so many, like, graphs are everywhere in the real world. You have networks, you have biological networks, social networks, here, web graphs, biological networks, knowledge graphs. So where you like Google, the Google search engine, it represents knowledge in graphs and relationships in order to answer some queries for you. For example, if you ask Google, what is the birthday of Obama? Then they have, like, internally they represent it as a graph, the Google knowledge graph, and they automatically scrap this information from the knowledge graph. For example, then it search the vertex Obama and search, like, relationship between other information, like certain days. For example, day could be also a vertex, and then they see, okay, it's associated via the relationship birth, and then they see, okay, Obama birth a certain day, and then they give you the information back. Okay, so it's like kind of for automatic knowledge generation, you often use graphs, and therefore arrays are also like application of arrays are also like these. All of those are also applications of arrays in a way, because graphs are based on arrays in most cases. Road networks, like if you have mapping networks, if you have neural networks or product recommendation relationships, like for example in Amazon, people who buy X also buy Y. They recommend some products based on previous purchase history. This is also based on an array. I mean you can easily draw another example here. If you have, like, if you buy, say, Harry Potter, so here you have some books. Yeah, so you may have some books like Harry Potter. What are some books? Some other books? Coffee Break Python, which is one of our books. We can have, say, from a book from Dan Brown. I don't even know. I don't read any novels anymore. So just read computer science books. So then you have another book, and then you have, like, person A. So say this is now Bob, and you have Alice with long hair, and now maybe Bob likes Harry Potter, Bob likes Coffee Break Python, but he doesn't like Dan Brown, and he doesn't like this computer science book. Okay, so now you know for Bob, you know what he likes and what he doesn't like. But now say you know from Alice, she likes Harry Potter, but she doesn't like this book from Dan Brown. She doesn't like the computer science book as well. Okay, so now you see, Alice is much like Bob. They are kind of the same. They have the same. They like the same product, and they don't like the same product as well. Okay, so but maybe you don't know whether Alice will like Coffee Break Python. Yeah, because I mean, you know everything else, but you don't know whether she likes this book or not. So for example, maybe she may have rated this book and this book and this book, but she hasn't rated this book. So you really don't know. This is a big question mark for you. Say you are Amazon, you need to know should we recommend Coffee Break Python to Alice. And now you use another user, Bob, who has similar interests as Alice, and use his rating in order to predict the rating from Alice, right? So you can do things like this. And how is it represented? It's a big table. It's a big array, basically an array of. So you have some. So for example, you could consider each column to be an array by itself. So you have or lines. Oftentimes you represent it with a list of lists. So you have this whole line or row will be one list, this one will be the second list, or array, this one will be the third array, and so on. So you have an array of array, and each inner array is basically one row of this array. And this is how you represent data. Okay, so each time you represent data, you are using arrays one way or the other. If you use pandas, if you use NumPy arrays, if you use any of those libraries, you heavily rely on arrays to implement this. Okay, so arrays are important. I think you get it now. So now the last thing to discuss is what are some runtime complexity of some operations. Some basic operations on this data structure are, for example, to access a given element. Yeah. So for example, if you have this array, let's go back to the first array that's least cluttered. So how complex is it to access an element from this array? So for some data structures, it's really complicated to access it because you have to go over the whole data structure to access it. But for arrays, it's very simple. You just take the index and you immediately get back the element. So it's like in one step. No matter how large the array is, it's very efficient because of the way arrays are implemented. It's very efficient to access individual elements. Okay, so therefore we say the average runtime complexity is linear. It's constant. So O of 1. Basically, yeah. So it's like a constant number, and it doesn't change if you change the size of an array. So even if you have an array with 1 million elements, you can access the 800,000th element very efficiently, very quickly. So like immediately, and it won't take any longer than as if you had an array with say 10 elements. Okay, so accessing the 8th element of a 10 element array has the same runtime as accessing the 800,000th element of an array with 1 million elements. Okay, so it doesn't grow with the size of an array. So let's have a small graph here. So say this is n. Yeah, n is the size of our elements, the number of elements in our array, and this is our time. So how much time does it take to access an element? So and now the great thing with arrays is that you have a constant relationship here. So this is the runtime function of accessing an element of an array. But searching a given element in an array, okay, this of course takes some time. If you have like 100,000 elements and you search for this particular elements, yeah. So, but you have many elements, so you know, okay, I have an element, I have an object Alice. I have this object Alice somewhere in my array, but I don't know the index of this element. Now this is really costly because now you have to traverse the whole. You start with the first one, you go over the whole thing, compare each element, whether it is the same, whether it is your searched element, and only if you find it you go back, okay, and you return the element. So in the worst case you have to go over the whole array, check each element, check each cell whether it contains the element you are searching for. So therefore, if you have growing number of elements, the runtime complexity of search will also grow. Okay, so therefore it looks like this. It is linear, so it will grow linearly. So it should be like a straight line. So if the number of elements double, your expected search time will also double. Why? Because you have to, like in the worst case, or also in the average case, you have to look at twice many elements in order to find your searched element, your specific element. So therefore, search has grows linearly with the number of elements. This is what this stands for. Also, how much time does it take to insert an element or to delete a certain element? Yeah, to delete a certain element, you first need to search it. Okay, so say you have the element Alice, you tell them, okay, delete the element Alice from your array. Now you have to go over the whole array, search it, and if you have found it, it's quick, you can just delete it, but you first have to search it. Okay, so therefore search and delete have the same runtime complexity, and also insert, it's the same. Yeah, so if you want to insert a certain element somewhere, you can very quickly go to the position. Yeah, so say you want to insert it position 20, maybe you want to insert it here, yeah? So like you want to insert an element or a certain element here, but the cells are fixed. So therefore, in order to insert an element, you actually need to override this given cell. So say, maybe let's have a better example. So this is your array. It is structured like this. Now you have some elements like 1, 3, 5, 8, 10. So it's an array of integers, something like this, 13. And now you say, okay, I want to insert my element 9 at this position. Now what you need to do is to remove this element and replace it with 9. But now you need to move it one way to this position. So now this element 8 is the new element of this cell, but now you need to remove the element that was previously there. So now you put this element here at this position. So put it like this. You remove the old element and place it in the next cell like this. And now you need to remove this element, create a new cell in the end, and place the old element of the previous cell into this cell. Okay, something like this. So in the worst case, if you want to insert an element at the first position here, you need to like shift all subsequent positions. It's really expensive operation because the way arrays are structured, they have this fixed number of cells and fixed cell indices. So if you, like mine previously, if you access an element at position I, you now want this, if you insert something, you now want that this element is accessible via position I plus 1. So and therefore, you really need to shift the element. There's no shortcut. You need to shift the element in the next cell, into the next cell, and therefore it can be really expensive. You need to touch, if you have a list with n element or an array of n elements, you need to touch n elements as well. So this can be quite inefficient. Therefore, it also has like a linearly growing runtime complexity. So as a rule of thumb, modifying an array is quite expensive. Yeah, you have seen this with if you want to insert something or if we want to search a particular element or so. So modifying it or doing some advanced stuff on arrays is really expensive, but relatively expensive, I should say. But getting a certain element at a certain position is really fast. It's very scalable, very fast. So if you have a pattern like read no write pattern, yeah, you only read elements at certain positions. Maybe you have stored the position separately and you simply need to access elements from your data structure. Arrays are like the most efficient thing you can think of. Okay, so I think we have handled all the important stuff of arrays as a conceptual, on a conceptual point of view. I could also go, I mean, there are many, like if you go into Python, arrays are basically lists, yeah. So if you want to use arrays, you usually use lists. The lists have many operations like append, clear, copy, count, extend, and so on. So many advanced operations. You can check them out. I have actually created a full tutorial on Python lists with say 20,000 words or so. So it's like a big tutorial. And I will give a link in the description below. You can check it out. So you can check out if you want to like learn more about arrays or lists in Python. And if you really want to use arrays in Python, then like multi-dimensional arrays and so on, then usually you should use NumPy arrays, because NumPy has an array implementation that is really powerful. It's really extends the functionality of lists by a big margin. So in Python, arrays are usually, the array data structure is either represented by a Python list, which is built in, or if you have some advanced requirements on your arrays and you really want to have an efficient implementation, for example, adding the values of two arrays and so on, some more advanced array operations on multi-dimensional slicing, and so you need to use NumPy, the NumPy library, and use their internal array data structure. Okay, thanks for listening to this video. See you in the next video. Bye.